Okay, so we're now ready for section 7.4, constrained maxima and minima. Let's first talk about kind of what they mean by constrained. So suppose we're a manufacturing company and we produce and we sell tables made of wood and metal. Each table will take so much wood to make it, and so much metal to make it, but we are restricted, right? We can't just make as many tables as we want. The number of tables we make depends on two things. One, how much metal and wood are needed to make each table, and also how much money we're allowed to spend on getting the wood and the metal. In other words, there's going to be a budget. That latter part, number two, is what we would call a constraint. So we need two functions in order to optimize, in other words, find either the maximum or the minimum based on constraints. We need the production function and the constraint function. There are two different methods, so let's look at them both separately. The first method is the substitution method, and if the constraint function is simple enough, we can solve for one of the variables, plug it in, use some algebra, and then rewrite it with one variable and then use our previous calculus methods to solve it. For example, suppose we're supposed to determine any extrema of this production function, f of xy equals x squared plus 4xy, and it's subject to the constraint of x plus y equals 10. Well, that constraint function is kind of nice, so I can get either of those variables by itself. Now, I'm looking at the first function. I will probably want to get y by itself because I've already got more x's there. So let's take that x plus y equals 10. We'll get y by itself. And now let's plug that into our f function. And now we've simplified. Well, now we've gone from two equations that we have to deal with down to one equation. And we can actually find the extrema here using our first derivative test and even our second derivative test. So if we take the first derivative of f prime, we would get a negative 6x plus 40. And remember, our critical values where we find our max and our minimum is where that first derivative is going to equal 0. So we get an x value of 20/3. Now, we can put it on a number line and test just to make sure to see if it's a max or a min by plugging in values, test values of f prime. Or we can use our second derivative. And since our second derivative is negative, remember that means it's concave down. So if our function is concave down, then that means that critical value is going to be at a maximum. So our extrema occurs, so we have a relative max at f of 20/3 for my x, but now we have to figure out what that y value would be. Well, remember up here, y is 10 minus x, so we can use that. And we can find the y coordinate at that relative max. Now, sometimes they want the full point. They want not just the input values of x and y, but they want the function value as well. So to find the function value, we plug those in to our f. So if we want the full relative max, it would be our two input values, 20/3, 10/3, and then our output of 1200/9. Or you can put the 1200/9 here. So that's the substitution method. Sometimes the constraint formula is not as nice and you're not able to get one of the variables by itself. I'm not going to give you any difficult constraint formulas to work with right here, but we need to practice this for if you do, see those in the future. So if you cannot isolate one of the variables, we use what's called the Lagrange multiplier method. Now, the definition the Lagrange multiplier itself, think of it as the change in production for every 1 unit increase in the constraint. So if your constraint's a budget, then, you know, if we increase the budget by $1, how will that affect our production? Now, the Lagrange multiplier, we actually use a Greek letter called lambda. Looks like this guy. Okay. And there's quite a few steps in the Lagrange multiplier. So what we're going to do is something a little bit different. We're going to actually focus on an example as we're going through the steps of this method. So in example B, it says the right company has a production function given by Q equals f of xy equals 200 x to the 0.6, y to the 0.4, where x is the number of units of labor. So basically the money that you're spending on people that are working for you. Y is the number of units of capital, and capital is usually money that you spend or invest in the company that helps you make things. Like, you know, the money that you're going to spend on equipment and supplies and factory, but not labor, anything that's not labor. And Q is the quantity of the product that you're producing. You know, how many tables are we going to make? Now, for each labor, each unit of labor, it's going to cost us $100. And for each unit of capital, it's going to cost us $150. And the budget for both of those is 60 grand. So first question is part A, determine the number of units of labor and the number of units of capital. In other words, how much money are we going to invest back into the company needed to maximize production? So remember when we talked about the tables, there's 2 things that affect how many tables we can make. The first one is the production function. Now, most of the time that function is actually going to be given to you. And it was in this one. We were given that f of xy equals 200 x to the 0.6 times y to the 0.4. That's our production function. We also need the constraint function. Sometimes it's given to us, sometimes it's described. So when they're telling us how much that labor and the capital costs and what the budget is, that's giving us information on the constraint formula. So each unit of labor, okay, and remember X is the labor, costs $100. So we're going to have $100 for every unit of labor. Plus, then it says the capital cost, and they told us that Y is the capital. So each unit of capital costs $150. So $150 times every unit of capital, and it cannot increase $60,000. Now, I know you might be thinking we could do the less than or equals to, but keep in mind, you want to use as much of your budget as possible. So go ahead and just set it equal to 60,000. Now, there are a few different ways to do this. I actually often use a different set of functions for this. It's the same thing, but I want to stay consistent with your book. What they do is they set the constraint function equal to 0. So that constraint function, and we'll call this guy G, okay, G of xy for your constraint. If we set that equal to 0, then we are going to have G of xy equals to 100x plus 150y minus that 60,000. We're going to use that F and that G, and if you remember back that lambda, you know, the Lagrange multiplier, to write what we call the Lagrangian function. And here's the formula for that. I'll write it in blue here, where you take the original function of the production plus lambda times your constraint function. So in this particular problem, we're going to have, and we'll use capital F for this function, and it's going to be in terms of x, y, and now also lambda as an input value. So we're going to use our first production function, so that's 200x to the 0.6 y to the 0.4 plus lambda times our constraint function once they've set it equal to 0, which is 100x plus 150y minus 60,000. Okay. You can distribute that lambda right away if you want to. A lot of people, that helps them in order to find step 4, okay? So step 1, we figured out what our two equations was, the production and the constraint. We went ahead and set the constraint equal to 0. A lot of times they will even give you the constraint with no equal sign, no 0. They'll just put this plus that, or this plus this minus that as the whole constraint. And then we write it in the Lagrangian function. And just again, the Lagrangian function, we'd use capital F equals the production plus lambda times the constraint. Okay, that's what this formula is right there. So now what we want to do is we want to find all three of these derivatives. And there's something special about this guy. We'll notice it here in a minute. We're going to find all three of those derivatives, set them equal to 0, and then we're going to solve a system. So we're going to find the partial derivative with respect to x first. Again, looking up here, I've got this function with x and this function with x. Everything else is a constant. So if I multiply, doing green, if I multiply the 200 times the 0.6, I get 120. Subtract 1 from that exponent, you get a negative 0.4. Y stays like a constant, 0.4. Plus, notice if I were to distribute that lambda is just like a number, then I would get 100 x lambda. And taking that derivative, we were left with just 100 lambda. We're going to set that equal to 0. And again, if you're like, what does that mean? If we were to distribute lambda to everything, this guy would be 100x lambda. So if you took the derivative of that x, you'd be left just with the 100 and the lambda. Now let's do the same thing, partial derivative with respect to y. This time we multiply the 200 by the 0.4, we'll get 80 x to the 0.6. And now the y, we're going to subtract 1 from that exponent. We get a negative 0.6 plus, notice we only have one y term there by lambda. So lambda times 150y, derivative of 150y would just be 150. So we get 150 lambda. That's also equal to 0. And I want you to notice what happens when we take the derivative, the partial derivative with respect to lambda. And I'll write it out here just so you guys see it. If we distributed that lambda, we would get 100x lambda plus 150y lambda minus 60,000 lambda. So if you took the derivative of all of that with respect to lambda, we would end up with 100x plus 150y minus 60,000. And then of course, we're setting that equal to 0. That might look familiar. I guess they're just trying to stay consistent, but the nice thing is this guy is also your constraint. So now we want to solve this system. And here's where we've got to be careful. I'm going to kind of reduce this just so I don't run out of room. One of the things that I recommend, since both the first equation, we'll say A and B here, both have lambda, solve for lambda. Or in this case, you can solve for negative lambda if you want, but solve for lambda and then set equal to each other. So if we're looking at this first equation, I'll change colors so we can see it a little bit better. Looking at the first equation, we would have 120x to the negative 0.4, y to the 0.4 equals, and I'm going to subtract that 100 lambda to the other side. So we have a negative 100 lambda. Now, on the left-hand side, notice that x has a negative exponent. So we can write that as 120 y to the 0.4, and then move the x to the bottom, make it a positive 0.4. And if we divide both sides by the negative 100, we would have a negative 100 there. So we've got what lambda equals. We can do that exact same thing for B. So for B, we have the 80x to the 0.6, y to the negative 0.6 equals a negative 150 lambda. Let's get rid of that negative exponent on the left. So that would give us 80x to the positive 0.6 divided by y to the positive 0.6, moved it to the bottom. And then we want to get lambda by itself, so we divide both sides by that negative 150. Now that both of those are set equal to lambda, I can set both of those equal to each other. So the 120 y to the 0.4 over the negative 100 x to the 0.4 is equal to, and then we can cross multiply. Don't forget to cross multiply means we multiply this way and we multiply that way. And remember, when we multiply variables, we add their exponents. So y to the 0.4 times y to the 0.6. Well, 0.4 plus 0.6 is 1. So that's why we no longer have those weird exponents, right? I'm going to go ahead and solve for x. So we divide both sides by that negative 8,000, and we get approximately, well, exactly 2.25 y. So we have a relationship between the x and the y, but we want to know the exact values of y and x. Now we're going to use constraint g, which is really the same thing as f of lambda, in order to solve for these variables. So the constraint, 100x plus 150y, we can write x in terms of y. So we would have 100 times 2.25y plus the 150 times y. We can go ahead and move that 60,000 back to the other side. And that would give us a total of 375y. And when we divide, we end up with y equals 160. So we have found the y value, which is, I think, what did we say? Y was the capital. We still have to go back and find what the x is, so we can still use the constraint. So we have 100x plus 150, but we now know our y is 160 equals 60,000. And then we found our x to be 360. This guy is our capital. And this guy was our labor. So we have our answer to part A. So we need 360 units of labor and 160 units of capital to maximize our production. And I believe that's what part A was asking. Yeah, determine the number of units of labor, number of units of capital or money to invest that's needed to maximize production. In part B, it's asking, what will that maximum production level be? Well, remember, we have a production formula. It was given. So we're going to plug in to the original production formula or function. And that was given f of xy, I think it was what, 200 x to the 0.6 and y to the 0.4. So we're going to plug in 360 for x and 160 for y. So we have got 52,054.65 products. Now, here's where I want you to be careful, and even in the homework, depending on how they answer it. Unless your production, it says that it's in thousands or it's in millions. Be careful with this because we cannot make 0.65 of a product. A lot of people were so used to rounding up or rounding down. And if we were just looking at this mathematically, we would round up, right? We can make 52,055 products. But remember, we only have so much money in our budget. So if we try to make more products, we're not going to have enough labor we're not going to have enough capital. We don't have enough money to make that. We're close, but we can't make that extra one. So that's why we round down. So this would be max production will be 52,054 products. Now, this last question, when it's asking if the budget for labor and capital is increased by $1, how will the production level change? Well, recall that the Lagrange multiplier is the change in production for every 1 unit increase in constraint. We need to determine what lambda actually equals, and we can use any of those up there that we have. Like, let's use the one from B. Remember, they're equal to each other, and that tells me lambda is 80x to the positive 0.6 divided by a negative 150y to the 0.6. But remember, we have values for x and y. Plugging in 360 for x and 160 for y will give us approximately negative 0.868. So that means if the budget is increased by $1, basically from 60,000 to 60,001, the production level will decrease by approximately 0.868 units. Now, again, we know we can't decrease by a portion of a table, whatever it is that we're producing, but also companies generally don't increase your budget by $1 either. So think of it this way: if you were able to get $10, then multiply it by 10, or it will decrease by 8 more products. So to maximize, we're going to practice what we just did on the Lagrange, using the Lagrange multiplier, but just with a basic maximize and that it's subject to that constraint. So we're first going to change that constraint function. We'll just write it as, G, that's our constraint, as x plus 2y minus 6. Then we want to write capital F. This is the Lagrangian function, the formula. So we start with our original 16 minus x squared, I don't know why I put it in parentheses, minus y squared plus lambda times our constraint when it's set equal to 0, x plus 2y minus 6. So if it helps to go ahead and distribute that lambda, you can go for it. If it was hard to see those derivatives, you can do plus lambda x plus 2y lambda, 6 lambda, however you guys want to put that lambda. Set the constraint equal to 0. We have found our formula. Now we need to find all 3 of those derivatives, partial derivatives. So capital F with respect to x, partial derivative. Derivative 16 is 0. Negative x squared would give us a negative 2x. Y is a constant. Then we get plus lambda equals 0. Partial derivative with respect to y, negative 2y plus 2 lambda equals 0. And then the derivative with respect to lambda is just going to be our constraint, but that's okay. We would get x plus 2y minus 6 equals 0. So now we want to solve this equation, this system. I would go ahead and solve for lambda in both of these. So in equation A, move 2x to the other side. In equation B, we're going to get 2 lambda by itself, add the 2y to the other side, divide both sides by 2. We just get lambda equals y. If we're solving, both of these equals lambda, which means y equals 2x. Okay, so we can use that substitution. Remember, we have one more equation down there. We can plug it into the g function. So if we have x plus 2y, let's go ahead and add that 6 to the other side. And then plug in y equals 2x. We get x plus 2 times 2x. We have found a value for our x. let's go ahead and find a value for the y using the same function. So we get x is 6/5, y is 12/5. And these actually turn out to be nice decimals, really. So we got, 1.2 for the x, and this would be 2.4 for the y. But again, if you don't get nice decimals, leave it in fraction form. So we found the x value and we have found the y value that would maximize this. But now we also have to find the output value. So we're going to plug it into the original. So f of xy, again, was 16 minus x squared minus y squared. So we want f of 6/5 and 12/5. Which is 44/5, which is also what, 8.8. So this guy maximizes, and it's a relative maximum at our x value, which is 6/5, y value, which is 12/5, and our output value of 45/5, or we can write it as 1.2, 2.4, and 8.8. We are done. Woohoo! Good luck. Talk to you guys soon. Bye.